On démarre dans une minute.
OK.
Okay, hello everybody, good evening. Hello for my friends from Tunis, France, Jeddah, Riyadh, and Dammam. And there is even some friends from Lebanon today with us. Okay, Nicolas Kielbasievicz is a PhD graduated at École Polytechnique, France. He's a research engineer at CNRS, the French Scientific Research National Center. And Nicolas is one of the main developers of the finite element library XLife++. This library is the result of an experience of more than 30 years, I think. And Nicolas is one of the main developers for these last years. Thank you, Nicolas, to accept our invitation, and you can start your talk now. Thank you.
Okay, thank you to invite me to speak about XLife++. And hello, everyone. Today I will present you the main features of XLife++. And as Nabil said, it is a very long history, starting in the 80s year, sorry, with the first code Lena, with the next software Melina in 89, and Melina was and Lena were in Fortran, and in 2004, first attempt to rewrite Melina in C++, Melina++. So these three codes were developed with Poems, my laboratory, and our very long friends from IRMA. Parallelly, there was other codes developed in the INRIA part of Poems, such as Montjoie in 2002. Coffee is still developed nowadays, in 2008 beginning, and FAM developed since 2009. Alors, Montjoie and FAM were developed by former PhDs of Poems, and both of them are now in INRIA, Marc Duruflé in Bordeaux Sud-Ouest, and Sébastien Impérial in INRIA-Saclay. The aim was to develop a unique software, and this was the beginning of XLife++ in 2010. And it was the year where I was recruited in this team. 10 years of development, but the first line only after 2 years of reverse engineering of Montjoie and Melina++, and the different releases of XLife++ until the 2.2 release from last weekend. So, what is XLife++? So as it was said in the title, XLife++ is the acronym for Extended Library of Finite Element in C++. And so it's dedicated to solve a wide range of problems based on PDE through variational approach with different finite elements methods and couplings of these methods. Finite elements, boundary equations, etc., etc. So all the information about XLife++ is on a website. So you have this URL on the screen. And particularly, you will find the installation steps. The compilation is based on the CMake tool, multi-platform application. And it's easy to use and easy to, and for us developers, it's very easy to provide binaries on different architectures. There is some GUI applications, there are some user scripts to help you to install and use XLife++. And some figures, now XLife++ is about 650 files, 230,000 code lines, about 60,000 comment lines, very important comments. The first documentation. You have a user documentation. Everything is available at on the website. User documentation to about 2,080 pages. The developer one about 400 pages, and at least 50,000 copy cups drunk during these 10 years of development. So XLife++, it's versatile and easy to understand, dealing with scalar, vector, transient, stationary, harmonic problems with absorbing conditions such as DTN, PML, and so on. It's a library adapted and destined to new developments and adapted for courses. XLife++ has integrated mesh tools thanks to the GMSH application. So it is very easy to define complex 1D, 2Ds, or 3Ds meshes, even with cracks. And it was one of the main features needed by the users of the parent codes of XLife++, so Melina++ and Monjoie. The specificity of XLife++ is couplings. And so we have very native Femben couplings. And these couplings, very few codes around the world offers it. XLife also manages a wide range of essential conditions. In fact, every linear set of essential conditions. It's an original versatile method. XLife also make available recent methods such as H matrices for BEM problems and Lagrange and edge elements at any order. And XLife has different wrappers to efficient external solvers, RPAC, UMFPAC, Eigen, Magma, and integrates parallel programming, mainly OpenMP, multi-threading with OpenMP. MPI is in progress, and through Magma, which is a linear algebra library developed for GPU, you have some GPU. Performance of XLife++ are rather good relatively to concurrent codes, but are non-optimals because XLife is a very general framework for a wide range of different methods. So it's less performance regarding to specific codes. Okay. Now I will show you different results through PHGs, for instance, obtained with XLife++. First of all, I will show you the work of Antoine Bérat with Anne-Sophie Bonemendia, Lucas Chenel, and Sergei Nazarov about invisible obstacles in a waveguide. Okay. Oh, just wait. The animation here show a non-reflexive obstacle. If you look at the solution in the perturb waveguide compared to the reference waveguide, you only see a phase shift. But we can also have invisible obstacles. Another kind of result is about BEM problems with electromagnetic waves. Here you have the EFIE with homogeneous Dirichlet boundary condition with the incident electric field on the left and the scattered electric field on the right on 3 planes. Next, you have wave propagation in plasmonic structures. This was a result of the PhD of Camille Carvalho in 2015 with Anne-Sophie Bonemendia and Patrick Sierley, and thanks to Colin Chambéron for the simulations. So the results are that there are waves, surfacic waves on the interface of the metal and the dielectric, and there are some black hole waves going to a corner. Next, one example of FEMBEM coupling. So we have Helmholtz problem with variable coefficients in some area, and this was used in the science fair in France during 2 years at ENSTA to explain with a very funny application the FEMBEM coupling. The application was to take a picture of someone, to transform the picture in the eta function, characterizing the media, and with XLife++ on this problem with variable coefficients to obtain a solution with a FEMBEM coupling. The area near the photo is FEM, and around was with the BEM coupling for the extension at any point. And this whole application lasted only 5 minutes from the picture taken with the camera and the results printed. And it was very interesting for everyone to take part to this exercise. Another example is about quasi-reversibility and level set coupling. It was the work of postdoc Dimitri Ponomarev with Laurent Bourgeois. And you have an example of detection of 2 obstacles from boundary data with a level set. Next, an example well known by Nabil. You have results with the half-space matching method. This is from UNS Chandrawijaja PhD from 2019 with Anne-Sophie Bonemedia, Sonia Fliss, and Van Baronian. This is wave propagation in anisotropic elastic media for aeronautics. And the aim, the purpose of this method is a FEM computation in the domain around the area of interest and to extend the solution by computing on each of the four straight lines, defining half spaces. And by computing of each half space and according the solutions, you have the main solution everywhere. And some results with two obstacles. Next, you have the most tricky application developed with C++. This is from Van Baronian PhD in 2009 with Anne-Sophie Bonemedia and Eric Luneville. Here is the variational formulation of the problem. The aim is not to read all of this, it's just to understand how complicated the problem is. And here is the main steps of the solution. You have computation of eigenvectors in 1D cross-section. You have next, you construct tensor kernels from numerical modes, sorry. Next, you have the 2D or 3D problem. And finally, you solve the problem. And you have here some solution. So it's an anisotropic elastic waveguide with a numerical hybrid DTN to simulate scattering in a plate with a stringer. Next application, recent application from Eric Luneville and Marc Lenoir about scattering of different obstacles with different scales. And this is about coupling BEM methods with optical physics. You have, for instance, Kirchhoff, with Kirchhoff coupling on the left and with Ray's method coupling on the right. And a full BEM solution in the middle, in the center. And the most recent results using XLife++ are from the PhD of Clément Beneteau that was defended last Wednesday. So PhD with Sonia Fliss and Xavier Claes about enriched homogenization with boundaries. So homogenization is to deal with periodic media. And the particularity of the PhD of Clément was to take into account a Dirichlet condition on a boundary. Taking into account this boundary, this Dirichlet condition, needed to enrich the asymptotic development through epsilon and conducted to a new way to deal with computations from the homogenization method, taking into account the semi-bands here. And finally, you have the final solution with the enriched model, which is quite good. So you saw the wide range of applications using XLife++. Now I will explain you through an easy example how to write a program using XLife++. So the model problem will be Helmholtz with Neumann condition for the beginning and directly after. Here is where you start before writing a line of code when you are using Life++. You have a minimalist main with the appropriate includes and the init function. The init function, a lot of background data, particularly messages that will be used in error messages, warnings, or just information messages in the language you want. So English, French, Spanish, or German, actually. Defining some global parameters such as the verbose level, etc., etc. Here is the Helmholtz solving the Helmholtz problem with X-Life++. The first part is the definition of meshes and domains. I will go back to each part just after. Next, you have the definition of spaces and unknowns. So you can see that objects are the mathematical vocabulary, the classical vocabulary. Next, you have the definition of the variational formulation, the bilinear form and the linear form. Next, you have the definition of the linear system to define the matrix for the bilinear form and the right-hand side from the linear form. You have the solving of the linear system and the post-processing and the visualization. So let's go back to the first part about mesh and domains. A mesh is defined from a geometry. Here you have a square, a cell type, here a triangle, a finite element order, here first, and a mesh generator. You have the structured mesh generator. You have a subdiv mesh generator, which is an unstructured mesh generator from some quite standard geometries. And you have the wrapper to GMSH that can deal with every kind of geometry. The square is defined from a vertex, so-called origin point, supposed to be the bottom left vertex of the square, a length, and the number of nodes per edge. You have different ways to define a square. This is the usual ways to define a square from the center, etc., etc., from 3 vertex, and it's the same way for every geometry available in X-Life++. A mesh can also be defined from a file, for instance, a GMSH file, or from a various set of geometries other than the square. Various sets of, for the geometries, you have various sets of geometrical parameters. You saw origin and length. I spoke about the center and about vertices. For the square, for instance, in different ways. You can define mesh steps by defining the number of nodes on each edge. This number of nodes can be different from an edge to another. Here it's twice refined mesh on the left and right edges. But you can also define a local mesh step on each vertex of the geometry. And so you can define different values of the mesh step in order to refine a mesh through a particular corner, for instance. Here for the meshes. Okay, now let's talk about the definition of the finite element space, unknowns, and test function. First, you have to define an interpolation. For instance, Lagrange standard of first order in H1 space. You can define interpolation up to under 2 when elements are prism or pyramids. You can define interpolation at any order on segments, triangles, quadrangles, tetrahedra, or ixohedra. In the current case, Lagrange standard first order, a shorter version for this definition is available. You have here, just say P1 as the second argument. About integrals. So we saw that for Helmholtz, the bilinear form can be defined this way with the ENTG function demanding the domain as first argument and the content of the integral as a second argument. In the second argument, you have a different set of differential operators. Here are some of the main syntax when you have variable coefficients. How can we define variable coefficients? This is just a sorry. This is just a
voilà
function.
ce que j'ai trouvé sur le web.
Shut up, Siri. This is just a function, a C++ function with a particular signature. First, you have one point. This is the point where the function will be evaluated. And you have an optional argument type parameters, which is some kind of container that can contain every kind of parameter. We will see just after how to use this container. So the return value of this function can be real or complex in scalar cases, but we can define vector functions, vector of real, vector of complex, and so on. And we suppose that is an example. We have two coefficients A and B, but instead of defining them inside the function, this could be the result of another computation, and we have to give them to the function in the main program. But you cannot change the signature of the f function. This is the context where we have to use the parameters object. So how we do it? First, the idea is to have in the PA variable argument, this is a sort of list of parameters with a name as a string. So PA with the string A, PA of string B, to be used here. Now, how can we add these parameters in the main program? Here you have the definition of a parameters object with a first element, A with value 2 as a real, and how to add other parameters, such as the parameter B here. Now you have a parameters object, and you have now to associate this parameters object to the function in a function object. The syntax is here. And now your variable myf is usable as if it was a real f function. Now in the integral, you can write for the right-hand side, for instance, integral on omega of myf times v. in a parameter object, you can set more or less any type of variable. Scalars, strings, matrices, and so on. Now, about integrals, you have at your disposal a wide range of quadrature formula, the classical Gauss-Legendre and Gauss-Lobato, the Grandman-Muller. Symmetrical Gauss are computed quadrature formulas. They are not unique for 1 degree, but we can compute them and we implemented these formulas to have quadrature formulas to other degrees up to 20. And the classical quadrature formula specific Hammerström, for instance. XLife++ chooses automatically what is supposed to be the most appropriate and accurate quadrature formula by taking the formula with the order low enough to approximate exactly finite element function, polynomials. And when there are variable coefficients, we take 3 orders more of this value. If you need to choose the quadrature formula by yourself,
je ne suis pas sûr de comprendre.
So Siri is still annoying. You can tell it as 3 third and fourth arguments of the ENTG function, as you see here. Okay, let's talk now about the solving of the linear systems. First, you have iterative solvers. The easiest way to use an iterative solver is the iterative solve function, taking the matrix, the right-hand side, the initial value, the kind of solver, and the names that we will give on the solution. Essentially used for the print to name the output file after. So you have a wide range of iterative solver, BCG, BCG stab, CG, CGS, GMRS, QMR, SOR, symmetric SOR, and so on. And each of these solvers has its specific routine, CG solve, GMRS solve, etc., etc. This also works with preconditioners by adding an additional argument, P, which can be defined as a preconditioner term. You have the LU, LDLT preconditioner, the diagonal one. You have the incomplete LU and so on preconditioners. And you can define your own preconditioner if you need to. So there are also direct solver through the direct solve routine, or if you need to have the factorization and the solving separately, factorize and factsolve routines. Also, for the direct solver, you have Gauss with or without pivoting, LU, LDLT, LDL star, or UMF pack, having each of them their specific routine. But direct solve choose the most appropriate direct solver according to the matrix properties, symmetry, for instance. And if UMF pack is available, use preferentially UMF pack as its more accurate. Just an ellipse here about eigensolvers from the same canvas. You have the main routine eigensolve that is hides two eigensolvers. First, an internal eigensolver with computational mode, the Krylov-Schur or Davidson, to have an eigensolver without installing an external dependency for Xlife++. And you have, of course, a wrapper to RPAC library that enables Xlife to solve any kind of eigen problems. Standard problems, generalized problems, symmetric, non-symmetric, etc., etc. And you have specific routines, eigen intern solve and RPAC solve. Of course, eigensolve choose automatically RPAC when RPAC is available. And we can export the results. Eigs is a structure that contains the eigenvalues and the eigenvectors. And the save2 file in this case will generate one file for the eigenvalues and one file per eigenvector. Now, let's talk about the post-processing, how to define an analytical solution. So you can define a solution, a constant solution, by defining a term vector from the unknown, the domain considered, the value, and the name. When we want to define an analytical solution, a variable analytical solution, instead of giving a constant, you give a function. Either directly a function such as uxa here, or a function object, as we saw earlier, when there are some parameters. And now for the visualization, mainly you have the save2 file routine by giving the base name of the file, the vectors, solution vectors you want to save. You can save several vectors in the same file, and list the file format. You have VTK, MATLAB, MSH, and row format is just to have only values stored one coefficient per line. From the same process, you can export a mesh, and also that's just a gadget, but you have the plot routine that calls save2 file and calls the application to display your file, calling either paraview for VTK, VTU format, or MSH, GMSH for MSH format. Okay, here are some results for this Helmholtz problem with GMSH, with paraview, sorry. The computed solution, the exact solution, and the difference between both of them with the filter calculator. So now we will go a little further in Xlife++ features by talking about essential conditions. What is the main difference for the previous example? If we have essential condition, we have side domains. So you have to tell the name of the side domain here, and to retrieve the domain in the domain variable just here. Okay, we have the main domain and we have the side domain. Now, you set the essential condition. For instance, U restricted to gamma equal 0. It's exactly the same syntax you will write if we are writing an article. Next, you just have to associate the essential condition to the bilinear form here when defining the term matrix. You have an additional parameter here. And it's okay. You have homogeneous Dirichlet condition for an Helmholtz problem. Now, if you want inhomogeneous Dirichlet condition, instead of saying U pipe gamma equals 0, you have here a function, another one function, with the same prototype, a point and eventually a parameters. And this function can be a function object when there are effectively parameters. So very natural. Here you have some results with inhomogeneous Dirichlet by saying that on all the boundary of the square, solution is equal to the exact solution we want. Now, if you want to add holes in the mesh, until now we were working on a square, and now we want a hole that can be a triangle. So now you define the square outside the mesh definition. So we define a variable S here for the square with the same parameters as before. You can define a triangle from the 3 vertices, okay? And now when building your mesh, you say S minus T. And your triangle is the whole of your square. You have the result here. And to say a little more about holes, the minus operator deals with real holes. Now, if you want that the hole is just another domain, such as in the right picture here, you say S plus T instead of S minus T. Very, very easy. And it works for with any kind of geometry, 1D, 2D, 3D, and sometimes for very advanced geometries, you have to force X-Life to consider hole, and it's also possible. Here's some funny example with 4 elements in the definition of the geometry here, and particularly for the smile that is defined from its boundaries to circular arcs, circ arc objects, and the smile is just defined with the surface from routine saying with plus the list of the boundaries, and it's usable as the other one. You can define one or several holes. You can define geometry from the boundaries for routine surface from and in 3Ds with volume from, and it works with everything. To solve a 3D problem, you just have to change the geometry by defining a 3D geometry, and the following of the code is just the same. Here you have the solution of the Helmholtz problem with Neumann on every faces of the cube. Still, how to define variable coefficients. I show you this before, but I show you this again. You have now K2 defined as a function. So you have to define a function K2 with a point and eventually a parameters. Eventually, because there is a default value that is the empty parameters. And now you set the K2 function as you want. So here is a constant, but you can define everything. Okay. We saw before that in integrals, you can define variable coefficients, but you have a wide range of differential operator. The first derivative, dx, dy, and dz, grad, div, curl operator, the surfacic version of these operators, the generalized version of the operators with coefficients, and you also have, for elasticity, for instance, the epsilon operator and every operators requiring the normal vector. And for instance, when you have cracks in your problem, the jump operator or the mean operator. So you can define any kind of problem with this list of differential operators. To end this part about integrals, let's see a more complicated example of mixed formulation. Here you have two unknowns, P and U. Nu is defined in H div space. This is a mixing of Lagrange P0 elements with Ravier-Thomas first order elements. You can mix unknowns as you want. Here you have the variational formulation. It's okay. You just have to be aware that P P and Q are vector unknown, so you have the scalar instead of the time operator. And you have here the solution on the square. So Xlife manages multi-unknown problems and also vector problems. The vector property can be set from the fact that you are using edge elements, Ravier-Thomas or Nedelec, or that you really want a vector unknown, such as a vector U, whose each component is, for instance, a Lagrange unknown. So what's coming next in Xlife++? This year, we will start effectively this part about domain decomposition methods, and it concerns the mesh partitioning and particularly wrapper to the library MPI. So you can define domain decomposition problem and use your computer resources if you have cluster at your disposal. Another part is the development of fast multiple methods. This is in progress with the wrapper to FastMMlib developed by Eric Darigrand-Lacarieux at IRMAR. And for the geometry engine, a new engine with a wrapper to the Open Cascade library, enabling you to use Boolean operations such as difference when geometries are partially included in other one and not totally as it's the restriction actually in XLife++. So difference, merge, etc. One funny example is very actual to the news is the coronavirus defined with this engine currently in development. Okay, that's the end of this presentation. If you have questions.
Thank you, Nicolas. Is there some questions?
I have a question, if you please.
Yes.
Yes.
Thank you. First of all, thank you for the nice presentation. It seems for me that this program is very similar to FreeFAM++.
Very similar? No, because FreeFrame, for instance, does not propose BEM problems and still less FEM and BEM couplings as natural as writing the variational formulation. There are currently some developments to add BEM in FreeFrame, but it's not so mature as in XLife++.
Okay. I want to ask about the complexity of this program. Do you think you know that if we are dealing in fluid dynamics problems, they need in higher dimensions, we need a very fast compiler. Do you think that this software will have a very low complexity comparing to FreeFAM, so we can extend our time interval and be faster and faster and to get more accurate results?
I'm not sure to understand the real purpose of your question, but FreeFrame is not a compiled language. It's just an application with a
yes.
Python-like language. Instead of XLife is a compiled language in C++. So it's easy to wrap XLife with other libraries as other softwares can do, even in other languages such as Python. I think about Phoenix and or Firedrake and BEM++ that are specific codes, Phoenix for the finite element part and BEM++ for the BEM. Okay. The placement of XLife if the finite elements software ecosystem is to enable very naturally the couplings. So you don't need to plug two or more than two libraries of software to write a code using either FEM computations or BEM computations, etc.
Okay. Excuse me, one more final question, if you please.
Yes.
About time-dependent problems. You didn't mention any loops for time problems, time-dependent time loops, I mean.
So yes, because this is very, as it is very natural to write essential conditions, is very natural to define time evolution problems because you have, I presented you the object term vector, you have the plural term vectors, and you can write u parenthesis n plus 1 equal u parenthesis n minus 2, etc., etc.
Oh, yeah.
So your time scheme is very natural
Yes,
to write.
yes, I understand it. Thank you so much. Thank you.
Is there other questions?
Yes, thank you, Doctor.
Yes, Fatih?
Doctor, I just want to ask, thank you for your lecture, very interesting, I so much appreciate. But I want to ask, can this thing be extended to multi-scale, or what is the relationship between multi-scale theory and ordinary finite element theory?
The multi-scale theory, I think X-Life is not on this level. In fact, dealing with a multi-scale theory is the work of the user.
Okay.
Now, when you have multi-scale, what you maybe what you think is the ability to interpolate solutions computed on coarse grids to more refined grids, for instance, or not?
Okay.
It's true that you have interpolations of solutions, you have projections, for instance, to export solutions of edge elements, because ParaView only deals with Lagrange finite elements. So we have to project the solution on HDiv or H curl to a Lagrange equivalent, just to the visualization, sorry. So you have a lot of tools available, even to interpolate on coarse grids or refined grids. In fact, we have such as, and okay, we choose, and it's very logical, the same approach as free frame with a variational approach by dealing with integrals and not with the main problems. This was, for instance, the purpose of Montjoie, one of the former softwares of X-Life, where you define, you wanted to, I want to solve Maxwell with axisymmetric, and you don't take other than this. X-Life, free frame, and other codes say that your problem is integral of u times v, grad u dot grad v, etc., etc. So it's at just a lower level. And it's the same for most of the tools available. Interpolation is one example for multiscale, for instance.
Okay.
Another example would be for the domain decomposition method. Okay, you can deal with solvers implemented with MPI. That's one step. But our purpose is to offer a wrapper to MPI directly, such as a user can set its communication between process with an easier way to define data to be sent or received from a process to another. From the X-Life level, such as sending one term vector and not this part of the memory, etc., etc. But if we have this level, then you can have an higher level, either a user-friendly level, such as a black box application or.
Is there other questions?
Dr. Nabil, just I want say thank you for Dr. Nicolas for his presentation. Good presentation. I think I am working with Dr. Nabil in the same college, Science Daman. Inshallah, we are working on the heat equation in three-dimensional. But Doctor, I want asking for your work here. Is it possible to add, for example, other source term in, for example, like laser equation, Gaussian, etc., in our or in your equations there?
Sorry, there were some noise in your during your speak. I didn't understand.
For example, if we have a matrix, three-dimensional matrix matter, for example, on which we have in the same time some pairs, and we have also to add. And we have to study or investigate the heat propagation inside of a matrix having some holes of porosity, like you said, holes, some pores inside with different shapes. And we have, for example, this in this matrix, we have some heat equations created by laser
I think one of the examples shown by Nicolas show a periodic structure, and I think you are talking about these media, porous media with the periodicity. Okay.
Okay, it's very easy to define this kind of geometries. I spoke about the plus and minus operators. You have the equivalence of the plus equal or minus equal, then can be used in loops. So you can easily define grids, 2D, 3D, of holes in a geometry.
Yes, it is interesting, Doctor. Thank you, thank you.
I have a question, Nicolas. Is there some in the solvers library? Is there iterative solvers where you can define the matrix by the product and not by the matrix itself? By just its product with a vector.
Alors, in fact, what I show you, yes, I will go back to the slide. It will be easier to explain. Yeah. In fact, you will use the second form here. Here with the CGSolve function. No, sorry. There is a third way where you define a specific object for the solver, and you can use the parenthesis operator on this solver, and it's quite similar to this syntax. But in fact, the solver only needs a matrix vector product, so-called mult-matvec, eventually another function, but you can use these solvers with your own matrix object and your own vector object. The only requirement is this function for the product matrix vector product.
Okay.
So for instance, you can have a linear system where the matrix part is defined as a sum of different matrices with some product with inverse matrix, etc., etc. So your matrix class will store the different matrix elements of the real matrix you have to compute. And by saying how to compute the matrix vector product, you can deal with these more advanced linear systems without assembling the global matrix.
Okay. Okay, if there is no other question, perhaps we can stop here. Yes,
Dr.
Kamal?
Dr. Nabil, I have a question
Yes, Kamal.
about, I thank Nicolas for my presentation. I have a question about the prismatic finite elements. It's already implemented in Xlife++.
Yes, up to order 2.
In 3D,
Sorry?
Is already implemented?
Yes, it's already implemented up to order 2 finite elements.
Okay, it's okay. Thanks.
Doctor, hello, doctor.
Yes,
please.
Yes, I want to ask 2 questions. I want to ask quickly. The first question is I want to ask if you have a linear system, at what point do you consider precondition to solve that linear system? Because I know from what I do on the lectures and what I have read, I think a system of equation you can use any of the linear system of equation to solve, maybe CGM, GM, ROES, and I don't know at what point do we use a preconditioner. That is the first question. Second question, sir.
yes.
Second question, I don't know if you can share this also this note and today's lectures with us.
Sorry, I didn't understand didn't understood the second question.
The second question is can you share this lecture, this video, this can you share with us so that we can have the video?
The video?
Yes, and the
recording.
The recording.
Yes, the recording will be available on the website.
Okay. So
if Nicolas give me the permission, of course.
No problem. I also want the video.
Okay.
Okay. About your question about preconditioner, I just said very briefly that you can define your own preconditioner object for the same reason as you can define your own pair of matrix and vector objects using our iterative solvers, just having the scalar matrix vector product defining in a certain way. You can define your own preconditioner object, just having how to apply the preconditioner on a matrix, and you can have whatever preconditioner you want, even preconditioners that are not defined as a matrix. You can have a preconditioner defined only through operators. It's more abstract preconditioner, but you can do this very quite easy in Xlife. It's foreseen. It's available. Yeah, I think there is an example of how to define your own preconditioner in the user documentation. But I know some of PhD students in Poems used this feature.
Okay, I think we have to stop. Thank you very much, Nicolas, to accept our invitation, and thank you for the conference. And perhaps we can schedule other sessions with XLive with other colleagues. Okay,
Thanks,
thank you very
Nabil.
much.
Thanks, Nicolas.
Thank
Thanks, Nabil.
you. Thank
Thanks.
you very much.
Thank you very much.
Merci, Nicolas.
Merci.
Dr. Nicolas? Doctor?
Nicolas?
Dr.
Yeah.
Nicolas? Dr. Nicolas?